All right, today we're going to be doing 5.2 growth and decay. We're going to start off with an example. I want to solve for the differential equation dy over dt equals 6 minus y. Now I'm going to go ahead and I know I'm going to have to take the antiderivative. However, before I do that, I need to move all the y's and the dy's to one side and all the t's and the dt's to the other side. So I'm going to multiply both sides by a dt. So dy equals 6 minus y dt. Now I need that y on the left side, so I'm going to go and divide by that. So then I have a 1 over 6 minus y dy equals dt. Now I'm going to go and I'm going to take the antiderivative of both sides. Some of you may recognize that's going to be one of the automatic shortcuts where it's natural log. However, you need to be careful because that says 6 minus y. So it's going to need to be a negative natural log. Let me show you by using u substitution. I'm going to let u equal the denominator. So if u equals 6 minus y, when I solve for dy, du equals negative dy. So the negative is going to go on the left side. So it's negative du equals dy. So when I plug it in, I have the integral of 1 over u times negative du. And then the antiderivative here is going to be t plus the constant. This negative is going to be thrown on the front. Now, when you take the antiderivative of 1 over u, it's going to be natural log of u plus a constant. Plug the u back in. So that's 6 minus y plus c equals t plus c. Now, we only need to have the c on one side, so I'm just going to leave it on the right side. And since we're solving for y, I'm going to throw the negative on the right side. So if I throw the negative on the right side, that's basically dividing both sides by a negative. So I'm left with natural log of 6 minus y equals negative t. And honestly, what if that constant was a negative? A negative will make it a positive. So it really doesn't matter. I'm still going to keep it as a plus c though. And then how do I cancel out the natural log? I'm going to use e. So I'm left with the absolute value of 6 minus y equals e to the negative t plus c. I'm going to go and I'm just going to leave it like that because I can't take off the absolute value, but at least I got y almost by itself. Let's try another example. Y prime equals negative square root of x divided by 4y. Now, keep in mind, y prime is dy over dx. I'm going to throw the negative on the top. I'm now going to cross multiply. So 4y times dy equals, this is going to be a negative. I'm going to write that as x to the 1/2 power dx. This will work out nicely because the y and the dy's are together and the x and dx is together. So now I'm going to take the antiderivative. On this side, that 4 is a constant. And then I'm going to add 1 to the exponent, and whatever the exponent is, I'm going to divide by it, plus a c. Right here, that negative is going to be on the front. I'm going to add 1 to the exponent, so 1/2 plus 1 is going to be a 3/2, which means I have a 3/2 on the bottom, so the 3 stays on the bottom, but the 2 flips up to the top, plus a constant. Now, I only need to have the constant on one side, so I'll leave it on the right side. I'm going to clean this up. 4 divided by 2 is going to be a 2y squared equals negative 2 over 3x to the 3/2 plus c. We are trying to solve for y, so I'm going to divide both sides by 2. So when I divide both sides by 2, right here the 2's cancel, and I'm left with a negative 1/3 x to the 3/2, and then the constant divided by 2 is still going to be some constant. And if you wanted to, you could technically take the square root of both sides. Now we're going to get into some growth and decay models. The rate of change of a variable y is proportional to the value of y. And we get this dy over dt is equal to ky. So dy over dt, that is going to be the rate of change of y. Where ky is going to be proportional to y. Theorem 5.1. Exponential growth and decay model. If y is a differentiable function of t such that the y is greater than 0 and y prime equals ky for some constant k, then y equals c e to the kt. Where c is the initial value, that's important to know, of y, and k is a proportionality constant. Now the exponential growth occurs when the k is greater than 0, and exponential decay occurs when the k is less than 0. We're going to go on to example 2. The rate of change of y is proportional to y when t equals 0, y equals 2, and when t equals 2, y equals 4. what is the value of y when t equals 3? I'm going to go ahead and I'm just going to sketch this. T is going to be the x-axis. So 1, 2, 3, 4. 1, 2, 3, 4. We'll go up to 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. This is going to be the y. So at t is 0, y is 2. And at t is 2, y is 4. So right here, this is going to be a growth. This is going to be a growth, an exponential growth. So automatically, the k has to be greater than 0. The k is going to have to be greater than 0. Now, I'm going to go ahead and I'm going to use the equation from the exponential growth and decay. The y equals ce to the kt. Now, right here, the y, so when the t is 0, the y is 2. So the y is going to be a 2. I don't know what c is. I don't know the initial value. Well, technically you do. We'll find it right now, though. E, the k, I don't know what the k is, but the t is going to be 0. So that's 0 times k. E raised to 0 power, because 0 times k is going to be 0. So e raised to 0 power is going to be 1. So I'm left with 2 equals c. So that is my initial value, which I could have actually pulled it off the graph. Now let's use the other data. So the y is going to be 4 equals, now we have a CE, the K, I don't know, but the T is 2, so that's going to be a 2K. I found out that C equals 2, so I'm going to go ahead and plug that in. So I'm left with 4 equals 2 e to the 2K. I'm going to divide both sides by 2. So then I get a 2 equals e to the 2K. Now the opposite of e is going to be ln, so I'm going to take the natural log of both sides. So natural log of 2 is equal to 2K. You are solving for k, so I'm going to divide both sides by 2. So natural log of 2 divided by 2 equals k. So my equation comes out to be, and this will be the entire graph, y equals c e, and then there's the k. The k is natural log of 2 divided by 2 times the time. So that's going to be the equation for any point on the graph. And then just to show you right here, if I take the natural log of 2, and I divide that by 2, I get a positive 0.347 or 346. And remember what we said? The k has to be positive because this is a growth. Now it says, what is the value of y when the time is 3? So now I'm going to plug in the number 3 there. So I have y equals 2 e to the natural log of 2 divided by 2 times 3. And do not try to reduce these because this is natural log of 2 first and then divide by 2. So I'm going to type this in the calculator. 2 e to the, my fraction. I have a natural log of 2 is the numerator. I have a 2 in the denominator. And then I also have this times 3. I'm going to round to 3 decimal places. So y equals 5.657. So this one is very similar. Here, I just want the equation. So find the exponential function y equals c e to the kt that passes through the given points. The first point is going to be 3 1/2. The second point is going to be 4 5. It's going to look something like that. So from here, I'm going to go ahead and I'm going to write my two equations. So this is the t, this is the y. So for the first one right here, the y is going to be 1/2. C, I don't know. E, the k, I don't know, but the time is going to be the 3. So this is going to be a 3k. So that's that point. Now this one right here, the time is going to be 4, the y is going to be 5. So I have 5 equals CE to the 4k. Now when you're solving this, it's going to be like solving a system. So what I'm going to do is I want the y's to be equal to one another so that I can just set the CE to the whatever power it is equal to one another. So I want to make this one a 5. So what I'm going to do is I'm going to multiply all of this by the number 10. So 10 times 1/2 is going to be a 5. 10 times here is going to be a 10 CE to the 3k. Now you see how both of these equal 5? So since both of these equal 5, now I can set the other side of the equal sign equal to one another. So I'm going to set the 10 CE to the 3k equal to the CE to the 4k because they're both equal to 5. So I have a 10 CE to the 3k equal to CE to the 4k. I could basically divide both sides by c, so c's cancel out. So I'm left with a 10 e to the 3k equals e to the 4k. I'm going to go ahead and I'm going to divide both sides by an e to the 3k because I want to keep the bigger side. So I'm going to divide by e 3k, divide by e 3k. So I'm left with 10 equals, right here when you are have exponents, you take the top exponent and subtract the bottom exponent. So 4k minus 3k is just 1k. And if you are solving for k, the opposite of e is taking natural log. So the natural log of 10 is equal to k. I'm halfway done. I now need to find out what the c value is. So going back to this equation, I have a 5 equals CE to the 4. Now the k, I know the k. The k is natural log of 10. Now right here, I can actually simplify that. If you use the powers of logarithm, that 4 is actually an exponent. So this is actually 5 equals CE to the natural log of 10 to the 4th power. Now e and natural log cancel out, and you're left with 10 to the 4th power. So 5 equals c times 10 to the 4th power. I'm going to divide both sides by 10 to the 4th power because I need to find out what c is. So right here, this is actually 5. And then 10 to the 4th power just means that you're going to have 4 zeros, which technically this is just 0.0005. So it asks for the equation. The equation is y equals c e to the k t. And if you wanted to, you could have also wrote this like this. That's the same as saying 1 over 200. That's the same thing. All right, last example. We're going to do a half-life problem. We need to complete the table for radioactive isotopes. So we need to find out what the initial amount is. The amount after 1,000 years. But they gave us the half-life in years, 24,100. And I'm giving you the amount after 10,000 years. So the equation that we have is the y equals c e to the kt, because we are talking about half-life. This is going to be your initial amount. Another way I'm going to look at this is as y equals y naught, because that's our initial amount raised e to the kt. So I'm going to go ahead and I'm going to use this equation, and I'm going to use me knowing the fact that it's a half-life. Okay, so right here, if this is a half-life right here, then I'm going to go ahead. The initial amount will have to be 1, and it'll have to equal the half-life, correct? The initial amount will have to be 1, and it's going to have to equal the half-life, so that's going to have to equal a half. So I'm left with 1/2 equals, my initial amount will be 1, and then I have E, and then the K I don't know, but the time I do know. The time for one of the half-lives exactly will be the 24,100. So I hope that makes sense. You are equaling half of it. That's why the initial amount is 1, and I know the exact time for a half-life. So now I can actually, oh, that's not T, that's a K. The time is the 24,100, so I'm solving for K. So since I'm solving for K here, I'm going to go and I'm going to take the natural log of both sides. So I'm left with natural log of a half equals, natural log and E cancel. I didn't do anything with that 1. I'm left with 24,100 K. I'm going to go ahead and divide both sides by 24,100, which is the same as saying 1 over 24,100 times natural log of 1/2 is equal to K. So that's what that gave me. Now I need to find out what my initial amount is. So I'm going to use this part now. Okay, I'm going to use this part. So here's the equation right here. The answer has to be 0.4. So I'm going to set 0.4 equal, I don't know my initial amount. I don't know my initial amount. E. Now your K, I know the K. The K is right here. The K is 1 over 24,100 times natural log of 1/2. And then the time in this case is 10,000. The time in this case is 10,000. Now I'm going to go and I'm going to type all that in the calculator. So I have a fraction. 1 is the numerator. 24,100 is the denominator. Times natural log of a half. And then I'm going to have that times 10,000. So I get a 0.4 equals the initial amount, E raised to the negative 0.287612938. Since I'm solving for the initial amount, I'm going to go and divide both sides by all this good stuff. So I have a 0.4 divided by E, and then I'm going to pull the answer from the top because I'm trying not to round. I'm going to go ahead and I'm going to go to 3 decimal places, so that's 0.533. So that's going to be your initial amount. So 0.533 equals the initial amount. Now I technically have my equation. I have a y equals the initial amount, e raised to the k, here's the k, t. So now I can find out what it is at 1,000 years. I'm going to go and I'm going to plug in 1,000 years now. So I have y equals 0.533 e to all this good stuff, natural log 1/2 times 1,000 now. Now that number is already in my calculator, so I'm going to leave it there. So now I'm going to hit times e. Now there's my exponent. I'm going to put my fraction in. 1 over 24,100 times natural log of 1/2 times 1,000. And I get 0. I'm going to go to 3 decimal places, 518. And then these are grams. So this is the amount after 1,000 years. And that's the end of the notes.